In the previous video, we talked about derivatives and some of the properties and how to actually find the derivative by using certain rules. And in this video, what I want to talk about is the chain rule, which is one of the main ones that we need to learn in order to perform complicated differentiation routines. So the chain rule is written as follows. We have the differential operator, which is just d over dx, which essentially takes the derivative of whatever function it is acting on. And in this case, we're going to have a compound function, which is a function of x. So that might sound a little bit confusing to you, but the idea is that you're going to differentiate the function inside first. So you're going to have g prime of x, which is just the derivative. This is a shorthand notation that we use for the first derivative of a function. And then what you're going to do is you're going to multiply this by the derivative of the outside. So you're going to multiply this by the derivative of the outside. So what are you actually going to do with this? Well, you're going to differentiate f with respect to the function g rather than x directly. Another way in which we can write this is, suppose that we have our compound function y and we want to find the derivative with respect to x. So we are going to differentiate dy with respect to another variable u. So u would be the function contained within y. And then we're going to multiply that by the derivative of the function u, which is the internal function, by dx. So in this case, du over dx would be equivalent to g prime of x. And dy over du would be equivalent to f prime of gx. This is essentially another way of writing it down. So this is what the chain rule is all about. To show you a few examples, let's start with the function y equals to x plus 3 to the power of 10. So you could expand this and then just take the derivative of each of the terms in the polynomial using the rules that we learned in the previous video. But obviously that would be very inefficient and would take a long time. So what we can do is we can use the chain rule to actually find the derivative of this. So we're going to write dy over dx. What is that going to be equal? Well, first of all, we got to identify what the two functions here are. So the internal function here could be g of x equals to x plus 3, such that we get g prime of x. We can use the rules of differentiation that we learned in the previous example. And here we're going to get 1, because that is the constant that is attached to the x. So essentially, if you have something like x to the power of 1, when you differentiate it, you're going to get this. Because remember that you're going to subtract 1 from the power and then multiply by the previous power. And this is the same as 1. And for the constant 3, because it is not attached to anything, you can assume that this is attached to x to the power 0. What is x to the power 0 minus 1? Well, that's just going to disappear. So basically what you want to do, because it wouldn't make sense to have an x at the bottom. So with constants, what we do is we just make them 0 when we differentiate them. So this is what the derivative of that function is going to look like. Now the function of g, so f of g, is going to be equal to the function g to the power of 10. So g is just this. And the derivative of f with respect to g is going to be 10g to the power of 9. So now that we have our two functions, our two derivatives together, what we're going to do is we're going to multiply them. So 1 times this is just this function, so we're going to get 10. We're going to replace g by the function of x, so x plus 3, and all of that to the power of 9. So this is the derivative, and you saw, like, just by doing a simple substitution here, we were able to get it without having to expand this into powers and a polynomial of order 10. And this is the method that I recommend you employ whenever you have a function within a function. So just to show you a few more examples, let's have y equals to cosine of x squared. So remember that in this case, x squared is the function that is inside, because cosine is a function that is acting on the outside. So whatever number you give x is going to become x squared, and then that number is going to become the input of the function cosine. So g prime of x in this case would be 2x, and then f prime basically would be whatever the function that we are differentiating here is the function on the outside, which is the cosine. If you remember from the previous video, we talked about how the derivative of a cosine function is equal to the negative sine function. And this is a function of g, so g remains untouched. So now our dy dx is going to be 2x times minus sine. So I'm going to put the minus at the front, and that's sine of x squared. And you saw that it just took a few steps to get to this point. So the chain rule is very powerful, and it is very useful, and it allows us to solve for many different types of functions. In fact, you can almost find the derivative to any function as long as it is well defined. Now let's do another example. Y equals to e to the power 3x squared. This one is a bit trickier because we gotta identify which one is the function acting on the outside. So in this case, when we have a power, we can assume that the power is going to be a function in itself. So let's have gx equals to 3x squared, such that g prime is going to be 2 times 3, that's 6x. So 2 minus 1 is 1, so it stays like that. And now f is just going to be the exponential function. So f dash is going to be what? Well, we notice that this is the same as saying the derivative of, sorry, that should be d over dg of the function e to the power of g. And we saw in the previous video that when you have this kind of function, the derivative is just going to be e times whatever constant is attached to that g, which is 1 in this case, and the e to the power remains constant. So this is going to be e to the power 3x squared. So now that we have that, we can find the derivative, and if I write it as y prime, that is going to be 6x times e to the 3x squared. So 6x times e to the 3x squared. And one thing that you might notice is that whenever you have an exponential function like this, what you do is you differentiate the power and you multiply the whole function by that derivative, and that will give you the derivative of the whole function. And just to finish on a final note with the chain rule, I am going to go through an example involving the natural logarithmic function, because we talked about it in the last video, and I was going to talk about it in this video as well. So let's have a function y equals to natural log of 9x squared. So what is this going to be equal to? Well, let's make g of x equal to 9x squared, such that g prime is going to be 2 times 9, that's 18, times x to the power of 1. And now f of g is just going to be natural log of g. So this is going to be equal to the derivative of g. So if we write this as, let's write f of g as ln g. So from the previous video, we saw that the derivative of a natural logarithm is the derivative of the inside. So in this case, the derivative of g with respect to g is going to be 1. And it is divided by the function itself, which is just g. So that means that f prime of g is going to be equal to 1 over 9x squared. So if putting that together, so our dy dx is going to become 18x times this fraction. So 18x times the fraction 1 over 9x squared. And we can perform a simplification here. So this goes with that and becomes a 2. And this x vanishes with one of the x's contained here. So this becomes 2 over x. And that is why, in general, for any function ln of f(x), we have the following: f of x, so f of prime, f of x. So we just differentiate the function side that goes to the numerator, and then in the denominator we just put the function as it is represented here. And these are just a few examples of how the chain rule works, but in general you can apply it to a whole different range of situations and different problems, and it's a very neat and very useful method that we can implement in a variety of cases. And in the next video, I'm going to talk to you about another important rule of differentiation called the product rule.